Great, so we're going to be looking at problem 3 from section 2.6, and this is going to involve graphing null lines in the phase plane. So there's a few parts to this. Part A asks us to determine and plot the equilibrium points and null lines for the system. Right? And then we'll go on and ask other properties about this. So in order to plot the equilibrium and null lines, we're going to ask, well, what are the null lines? So recall, to find a null line, we have to set each of these equations to 0. So if I want to find my V null line, or the vertical null lines, and so these are isoclines on which the slope is directly up and down. Well, if the slope's going directly up and down, right, then your x isn't changing. So that's when you have 1 minus x minus y, your derivative of x with respect to t, when that's equal to 0. So this gives you one real line. So let's think about how would I set this up. Well, maybe I just write it as y equals 1 minus x. So this will give us a line in our xy plane. And I'll graph that in just a second. But while we're thinking about it, you'd also want to talk about the h null line. So I said, this turns out to be only one for the vertical null lines. In this case, the horizontal null lines will occur when you have your derivative of y with respect to t when that's equal to 0. So this is 1 minus x squared minus y squared is equal to 0. So that's what we want to graph. So that's what we want to graph on our picture. So let's come over here a little bit. I'll maybe actually zoom out a tad. So let's go ahead and put two axes here. So since we're doing stuff with a phase plane, we're no longer doing stuff with the y versus t axes, but we're going to do x, y. So sort of think maybe just go back to back to algebra. All right. So for the first one, for the v null lines, I'll maybe do this one with a yellow shape, since I did the equation in yellow. So that's given by this line, which goes through 0, 1, and then has a negative slope. So it goes something like this. And maybe I should go sort of back this way as well. So if that is your sort of 1 or 0, 1, 1, 0, so there's your V null line. So what might be helpful to recognize is along this, all my slopes of my solutions are vertical. Now for your H null lines, you might recognize that's actually a circle. It's actually a circle. So I'm actually going to zoom in to help myself draw a nice circle here. So we did that in green. So it's a circle with a radius of 1. So it kind of goes through these like so. So maybe if I had a lot of forethought, I would have drawn this one a little bit bigger. So here's my H null line. So every solution that goes through this circle has a horizontal slope. So this is really, this is like terrible. I really should have zoomed in more on this one. But there you go. So there's our system graphed, and these are our null lines. And so the equilibrium points, well, that's where an H null line and a V null line intersect. So we have two of them. So I'm able to do my equilibrium points in blue. So I have one right here, and I have one down here as well. So what they ask us next to do is to show the direction of the vector field between the null lines, sketch some solution curves, and then talk about stability and instability in these cases. So what we're going to do, so let's think about each of these regions. So we have a region sort of above everything. We have this region sort of between these two null lines, this region down here, and a region on this side. So what's interesting about graphing these is, let's look back at our equations for a second. So taking the top equation right here, we have on our yellow line when this equation is equal to 0. So the only way to go from positive to negative is to cross this yellow line, which tells me everything on the other side of the yellow line, say on the top above the yellow line or below the yellow line, will have the same sign for the derivative of x with respect to t. So let's take a test point, for instance. Say we took a test point up here. So think I would maybe let x be 0 and let y be 10. Take something that's obvious. Well, if that were your test point, then your equation with 0 and 10 would be negative. So that tells me that everything that is above is going to have your x-coordinates, or the derivative of x will be negative. So that's going to tell me everything up there is going to be going sort of to the left when it comes to your x values. And then below will be the opposite. So below, all your equations are moving to the right. And this will be true even inside our circles here. All right, so those are your x coordinates of your vectors. Now let's go consider our y coordinates. So our y gave us this circle when it set it equal to 0. So if we pick a point that's outside the circle, it will give us a certain direction for our y, and then a point inside will give us maybe the same, perhaps a different one, because the only way to go from positive to negative is to cross 0, so to cross this green circle. So let's take a point outside this green circle, and I'll also graph that in blue along with these lines that with these arrows I've already drawn. So for our y components, if we pick a point outside the circle, so say you pick 0, 10, for your x and your y. Well, 0, 10 will still give us a negative value. So that tells me outside the circle, since that's where I pick my point from, my y values are going to sort of be negative. They're going to point downwards. So each of these arrows on the outside has something pointing downwards with it. Now, if I were to take a point on the inside, take an easy point. Say take the point 0, 0. Well, then my slope here is 1, which is positive. All I care is that it's positive. So that goes up. So that tells me inside of the circle, let's zoom into it, my vectors are pointing in the up direction. So sort of up. So each of these vectors, then, I have my x and my y components drawn. I'm going to pick a different color. Let's say I did it in white, and say, well, each of these then is actually pointing in the direction of the white arrow here, more or less, right? So we're just sort of getting a sense. It might not be pointing exactly at this 45 degrees downward motion. It likely isn't, but it gives you a sense of the direction in this vector field. It's also good to consider, well, looking on our points as well, right? So if you are on this yellow line, they're vertical, but are they pointing up or are they pointing down, right? So think about that. Well, we already said for when you're on the outside of the circle, right, everything's pointing down. So each of these, I might even modify the arrows I have on there in their own color, right? So each of these arrows on my null line, they're vertical, but since on the outside they're going down, so these are all arrows pointing down on the outside. And then on the inside on this line, the arrows are pointing up. Likewise, on the green circle, we've said that everything above that yellow line, right, points to the left. So I'm going to use my green color here and say these horizontal lines are actually all pointing sort of inward. This gets a little messy. I apologize for that, but these green arrows are all pointing inwards on that circle. And then when we're below the yellow line, they point to the right. By inwards, I should have said to the left. All right, so there is a sense of the whole vector field. Oops, I just might add a couple around. So the next part of this question asks us to sketch some solution curves, starting near but not directly on these equilibria. And so here I'm going to zoom out a tad and sort of say, well, we have this sense that if we're, say we're near this blue line, I'm sorry, this blue line, what am I saying? Near this, the top equilibrium, so there's two. There's sort of this one right here at 0, 1, and there's the one down here at 1, 0. We may also want to talk about now then, what do solutions look like? Well, it looks like if I'm around here, so up above, it looks like they're going to be tending down and to the left, so sort of tending towards this. So I might sketch, let's say we did it in red, an idea of a solution curve. So it's going to come down sort of near here, and it's going to move towards it. So something like this. All right, and then maybe it would stay there. If I started over here, so maybe it would go something like this. Maybe it goes towards that as well. Right. You could also, if we chose, put in even more points in this vector field than just the overall sense of it. And we would find that we actually have some things that come down. So start over here, they come down kind of like this. Some are going to go in here, but once we're inside, you see it actually points us back up. If we had come down and we're inside over here, it ends up pointing us back the other way. So it looks like a lot of these solutions are going to tend towards this top point, making this one right here a stable equilibrium, since it is attracting all these values. What about near the ones down here? Well, if I start right here, for instance, well, I'm going to go down is the direction that we're indicated. If I started over here, we'll go in there, and it seems like it's also going to go down as well. You might get lucky and maybe one will kind of get near there. But most of the things that are nearby, right, if I start over here, for instance, it's like, oh yeah, that might want to go there, but as soon as it hits there or gets close, it shoots up again. It may even tend to this other equilibrium up here. So this is getting kind of messy. That's one of the downsides of this process, is it does get pretty messy. So if I were to do this video again, I would have likely drawn the diagram much larger, right, in reference to how thick my lines are here. But the overall idea here is you can get a sense of the way the solutions move. It's good to also remind yourself that since we are not explicitly graphing time, since we have x and y here, I don't know how fast solutions go along any of these different curves. But we do know that if they're near this one, this equilibrium point, they will tend towards it. If they're near the one down here, they'll tend away. Right? So making that bottom one, we should just mention that this bottom one is unstable, since that's what part D asks us.